The previous example omitted the distinction between update and evaluation events. We'll now go through the same example, this time distinguishing between update and evaluation events. And for clarity, we indicate an update event using the color purple and an evaluation event using the color green. So for example, if this is our active event queue, we have an evaluation event, an update event, and an evaluation event. For an update event, we indicate it as follows. C is the signal to be updated, and the update is such that the signal changes from an X to a 0. So the X goes to 0. We also use the following rule that events on separate lines can be completed in any order. So in this example, we have 3 lines, each containing an event. And for the active event queue, any one of these events can be selected. In other words, they can be completed in any order. Whereas for the case of the active event queue looking like this, when we have events on the same line, they must be completed in the order listed. So in this case, the update event must be completed before this evaluation event. We use a table to capture the events that occurred during simulation. The table has 3 columns. We have the active event column, the future event column, and the event that's being processed. A row in the table, such as the one shown here, contains the event that's currently being processed, and the second column entry contains the state of the active event queue after the event in the first column has been completed. And then the third column contains the state of the future event queue after the event in the first column has been completed. We use a table to capture the steps during the simulation process. Just a recap as to what the simulation contains. The yellow area shows all the processes, reg variables and wires that are part of the simulation, and the code in the grey box is just for the test bench, so we can see what the statements inside the initial construct are. At the start, we have the initial construct added as an event to the active event queue, and note we start with the time t is equal to 0. The subscript on the initial indicates the next statement inside the initial to be carried out. So at the start, this is the only event in the active event queue, and the initial construct with in1 is the first statement to be carried out. When the simulator carries out this statement, the right hand side is evaluated. It evaluates to 0, and then that produces an update event on in1. So you can see we have a new event added to the active event queue, the update event, and we still have to continue the processing of the initial construct because there are further statements in it. So we have 2 events in the active event queue, an update event and the initial construct, and the next statement in the initial construct is this statement here. So at this point we've processed the first statement. Now you'll note here that the 2 events, this update event and evaluation event, are on the same line, so they must be processed in the order listed. Now the reason for that is, if you remember when we spoke about an initial construct, that the statements are always executed in order. So that means you cannot go on to this statement until this one is fully completed. And for that reason, the update event must occur before we continue with the initial construct. Therefore, we've no choice. The next event to be processed must be this update. So we take this event here. That means we take it off the active event queue. We process it. When you process it, changes from X to 0. That then triggers the addition of a new event to the active event queue, assign A is equal to in1. So this new event gets added to the active event queue, and this is an evaluation event. We now have 2 events in the active event queue. we have our initial, and we have our assign. The simulator is free to pick either one as the next event to be handled. Let's pick the assign. So this event is then handled. Assign A is equal to N1. N1 is evaluated. It's 0. That then produces an update event. A will be updated, and that update event is added to the active event queue. And we have two events now in the active event queue. Again, either one can be selected. So let's pick the update. That's now processed, and when this is processed, it causes an update to A. So A is now updated from X to 0. And when A is updated, you'll note that that's a trigger to add this assign statement to the active event queue, and that's what's added here. Again, we have two events in the active event queue. Either one can be selected. Let's go with the initial. So we continue executing the initial at N2 is equal to 0. This expression evaluates to 0, and it produces an update event for N2. So this is a new event that's added to the active event queue, and this must happen before we proceed with the initial construct. Again, for the reason that the statements inside the initial must complete in order. So at this point, we have three events in the active event queue. We have one event on this line and two events on this line. So either line can be selected, and we note if we take the second line here, which contains two events, the update event has to occur before we continue with the initial. Let's go with the event on the first line. So we now take this event and process it. And when it's processed, the right hand side is evaluated. A ended with B. Now you'll note in this case, B has the value X and A has the value 0. So 0 ended with X will always be 0. So the value 0 is the result of this expression, and that produces an update event on C. This new update event is added to the active event queue. At this point, we have three events in the active event queue. On this line, we have two. We've got an update event and an evaluation event, and on this line, we have an update event. Either line can be selected. So let's say we go with the first line here. That means we take this event and handle it, and this is an update, so we update N2 to 0. So when we do that, N2 changes from X to 0. And an update on N2 will trigger this assignment to occur. So assign B is equal to N2 is added to the active event queue. And at this point now we have three events. Each is on its own line, which means any one of those can be picked. There's no order associated with these three events. So let's say we take the first event, which is this evaluation event. It's the initial construct at statement #1 string display. So this is the display system task, which just puts some output to an output window. But note, it cannot occur until after a delay of 1 time unit. So our current time is t is equal to 0. And if we wait 1 from that, that means this will be scheduled in the future event queue at time t is equal to 1. So the initial moves to the future event queue. We insert an event into the future event queue, and we're left with these two. So the purpose of this example is to just illustrate the way in which the simulation proceeds, distinguishing between updates and evaluation events. Now, if we contrast this with the previous example, where we did not distinguish between update and evaluation events, this appears to be more complex when we distinguish between update and evaluation events. And a natural question that arises is, why would we want to distinguish between update and evaluation events? Now, in the Verilog language, there's one key reason why this is necessary, and it has to do with what's known as non-blocking assignment statements. And these are very important when you work with sequential logic. So in terms of understanding the simulation process, it's best to combine the update event as part of the evaluation event. But when we do come to non-blocking assignment statements, you will appreciate the reasoning for having a separate update event.